In this video, we're going to look at topic 83, example 3, graph transformations of cubic and quartic apparent functions. So one of the things we're going to need to reference here is we're going to be looking at y is equal to a x minus h plus k. And there'll be some type of exponent here. For these examples, we're looking at cubic and quartics. So that exponent would be a 3 or a 4. But these rules apply for absolute values, for quadratics, for something to the third, fourth, fifth power, and so on. Right, so it's been a little while, so I want to refresh our minds here. If we have a, so a determines a couple different things. If we have a negative a, we want to remember that there is a reflection. If a is greater than 1, there's a stretch. And if a is between 0 and 1, there is a compression. Now, some people might reference absolute values for certain parts of this. We're just going to go by negative a is greater than 1, or whether it's between 0 and 1. It is possible to have a stretch and a reflection, or a compression and a reflection, but you cannot have a stretch and a compression, obviously, at the same time. All right, my h value, that is my horizontal movement. But remember that this is backwards. So if I'm adding h, let me fix that. So plus h would be a shift left h units. And if you're subtracting h, that would be a shift right h units. And then finally, my k value controls vertical shifts. So plus k, these are the easy ones. There's a shift up k units, and minus k is a shift down k units. Okay, so keep this in mind here. We need to reference this for problems A and B. So the question, how do transform graphs compare to the graph of the parent function? So the parent function is anything where your numbers are removed. So if I just pretended that these were not here, x to the fourth would be my parent function. In part B, if I just got rid of the 5, the negative 2, and the plus 4, x cubed would be the parent function. Okay. So let's look at 3x to the fourth minus 18. Now we want to ask ourselves is what does the 3 represent? Is that a, h, or k? Well, the 3 is going to be a. So a would be equal to 3. Now the minus 18, we have to be careful. Ask yourself whether that's in or outside of brackets. It is outside the brackets, so that represents the minus 18 would be k. And if you really wanted to say anything about h would actually be equal to 0 in this case because there is no shift left or right. If you wrote this full thing out, it would look something like this if you wanted to include h, right? That is h. But we don't need to worry about that because it's not part of this problem. So k is minus 18. Since a is equal to 3, that tells me that there is a stretch. Because a is greater than 3, so there is a stretch by a factor of 3. K being equal to negative 18, that tells me that there is a shift. Remember, this is vertical. K is up and down, so there's a shift down by 18 units. That's it. H equals 0. There is no horizontal shift. Right. You don't really need to state that, but since we're going through this as a lesson, it's good to just kind of note that. So there is no horizontal shift. You should be able to do these without the graphs. Obviously, we didn't need to look at the graph to figure out what a, h, and k were. But if you do look at the graph, you'll notice that this blue one, our f term, shifted down 18 units. And it kind of got pulled a little bit taller. So it kind of got narrowed. So that's why there's a stretch. Let's look at part B. So in part B, we have an a value of 5. Right, this 5 here is in place of a. So a is equal to 5. We do have an h value, and we do have a k value. K is 4, so that's pretty easy. And then h is going to be a value of 2. All right, so h, let's use the same colors. And let's say h is 2. All right, we need to be careful here, especially labeling them. But h is a value of 2. That subtraction, that minus 2 is kind of what, gets a little bit tricky. So you need to be careful with the shifts in that minus 2, positive 2, and determining whether h is 2 or negative 2. It will take some getting used to. Just if you're looking at the expression, the function itself, remember it's opposite. But if you're labeling h as 2, that's going to be a shift in a certain direction, and you'll get the hang of it by looking at the graphs if necessary. Okay, so a being equal to 5, that causes a stretch, right? It's greater than 1, so there's a stretch by a factor of 5. I'm going to go to k first because that's a bit easier. K being a positive 4, we're going up, right? So that would be a shift up by 4 units. And then the h value, be careful here. H is just 2, so that is a shift right. But in the actual function, it's minus 2, which also causes a shift right. So there would be a shift 2 units, shift right. Let's use the same phrasing. Shift right by 2 units. H is always the most confusing one. All right, the reason for that is in the function here, it looks like a minus 2, right? So that tells me that it's going to go right. But the actual h value, because the actual vertex form is minus h itself is only a 2. That's why things wind up moving right. If we actually look at the values, it makes a little more sense. If you look at the function itself, then it is backwards. Okay, so be very careful with your h values. A and k become very easy to work with, but h tends to mix up a lot of people. So do be careful. Sometimes it's helpful to graph it. You can use a graphing calculator to do that and compare it to the original to see whether it goes up, down, left, or right. Visually, it can be tough to see the stretches and compressions at times, but the shifts themselves are usually pretty easy to figure out. Right, if you notice, this point here went to the right 4, I'm sorry, to the right 2, and then up 4 places. Your x and y scales are not the same there for either graph, so be careful with that. I'm done talking for that. Hopefully I didn't over-explain it, and you don't have any issues with it.